year is 1986, Cape Canaveral. Just seconds after liftoff, a massive rocket explodes in the sky. Millions of people watch the disaster unfold live on television. Later, the investigation would show that the cause was a small rubber part worth only a few dollars. Because of the extreme cold, it failed to work the way it was supposed to, and that was enough to destroy one of the most complex machines ever built by humans. The disaster once again forced engineers to think about a question they had been debating for decades. At first glance, a rocket seems fairly simple. A huge tank full of fuel, an engine at the bottom, and that is basically it. But in reality, everything is far more complicated. Every single part has to work perfectly, because even a small mistake can lead to disaster in the very first minutes of flight. So how are rockets actually built? And is it true that 90% of their mass is fuel? Imagine building a truck the size of a skyscraper just to deliver a single small box of candy. The truck weighs hundreds of tons, yet its entire mission is to carry that tiny package. It sounds like the fantasy of a mad engineer, but that is the harsh reality of spaceflight. It all comes down to one fundamental law of physics, a law that even today's most advanced technology cannot overcome. The great scientist Konstantin Tsiolkovsky developed an equation that became both a blessing and the greatest curse for rocket engineers. It describes the mathematical relationship between a rocket's mass, the speed of its exhaust gases, and its final velocity. The real challenge is that moving a massive fuel tank requires fuel. But that fuel has weight of its own, which means you need even more fuel to move it. And that extra fuel also has weight, creating a chain that quickly spirals out of control. This vicious cycle forces engineers into extraordinary compromises, reducing the payload to a mere 2 or 3% of the rocket's total liftoff mass. To outsmart the unforgiving laws of physics, they came up with a simple but brilliant solution: build rockets in stages. As soon as a massive fuel tank runs dry, it is jettisoned in flight, instantly shedding tons of dead weight. The greatest example of this idea in the 20th century was the legendary 3-stage Saturn V, developed under the leadership of the brilliant engineer Wernher von Braun during the 1960s for America's lunar program. Standing 111 meters tall, the giant weighed nearly 3,000 tons at launch. About 2,700 tons of that was nothing but fuel and liquid oxidizer. The enormous first-stage tanks held more than 2 million liters of kerosene and liquid oxygen. All of it was consumed in just 150 seconds as 5 massive engines roared to life, lifting the rocket to an altitude of only 67 kilometers. That incredible firestorm at liftoff served just one purpose: to accelerate and deliver a spacecraft weighing only 45 tons to the moon. It was a dramatic demonstration of just how unforgiving the laws of spaceflight really are. Those enormous amounts of propellant demanded equally enormous tanks. But if the tank walls were made thick and strong, the rocket would never leave the launch pad. Every 100 grams saved meant a few more precious meters per second of velocity once the vehicle reached orbit. That is why engineers began designing tanks with walls so thin they resemble an aluminum soda can far more than the armor of a heavy military vehicle. If you step on an empty soda can, it crumples instantly under your weight. But if the can is sealed and pressurized, it can easily support the weight of an adult. Modern rockets are built on the very same principle. In some areas, their metal skin is no thicker than an ordinary kitchen knife. Engineers use what's known as a pressure-stabilized structure. Instead of relying on thick internal beams, heavy frames, or reinforcing ribs, the rocket's strength comes from pressure inside the tanks. Pressurized helium, or evaporating nitrogen, continuously pushes outward against the thin walls, keeping the metal under constant tension and giving the entire structure its rigidity. This makes it possible to build tanks from ultralight aluminum-lithium alloys just 3 or 4 millimeters thick, even when the rocket itself is 9 or 10 meters in diameter. Welding sheets that thin is an extraordinary feat of precision. Every weld is inspected with ultrasound and X-ray imaging to detect even the tiniest microscopic cracks. But this incredible weight savings comes with a frightening downside. If the pressure inside the tank drops by even a small amount, the rocket can lose its structural strength and collapse under the weight of its own upper section. A dramatic example came in 1960, when an American Atlas rocket stood on the launch pad without fuel. Because of a malfunction in the tank pressurization system, the internal pressure suddenly began falling below the critical level, causing the vehicle to lose its rigidity. To the astonishment of the engineers, the giant steel cylinder, as tall as a 10-story building, slowly began to wrinkle. It lost its structural strength and literally folded in half under its own weight, collapsing into a twisted heap of scrap metal. The incident proved once and for all that a rocket can hold its shape only when its internal pressure remains perfectly balanced. But maintaining that delicate balance inside an ultra-thin structure is only half the challenge. The real nightmare begins when substances at radically different temperatures have to exist side by side inside the same vehicle. Separated by nothing more than a thin sheet of metal, the freezing cold of liquid oxygen sits just inches away from the roaring inferno inside the engine. Keeping those two extremes under control makes a modern liquid-fueled rocket engine one of the most extreme thermal environments on Earth. Inside the combustion chamber, temperatures exceed 3,000 degrees Celsius, far beyond the melting point of virtually every known metal and alloy. To keep the engine from melting within seconds, engineers rely on a brilliant technique known as regenerative cooling. Instead of fighting the heat, they turn the cryogenic fuel itself into a protective shield. Before reaching the combustion chamber, liquid kerosene or hydrogen is pumped under enormous pressure through thousands of microscopic channels built directly into the engine's double walls. The ice-cold fuel absorbs excess heat from the glowing metal, cooling the engine from the inside while warming itself in the process, making combustion even more efficient. In the late 1960s, Soviet engineers, led by Nikolai Kuznetsov, faced the full complexity of this challenge while developing the powerful NK-33 engines for the Soviet N-1 moon rocket. They had to create unique copper-chromium alloys with exceptional thermal conductivity and coat the inside of the combustion chamber with an ultra-thin layer of specialized ceramic. Without it, the superheated oxygen would burn through the metal almost instantly. Even the smallest flaw in the coating process, or a tiny speck of debris blocking a cooling channel, could cause the chamber wall to burn through in a fraction of a second, triggering a massive explosion on the test stand. Every engine firing was a delicate balancing act on the edge of disaster, with nothing but a paper-thin metal wall containing an inferno. But even the best heat shields and the most advanced alloys are useless if enormous volumes of cryogenic fuel cannot be delivered to the combustion chamber fast enough. To force a ton of propellant through tiny injector nozzles every second, pressure inside the tanks alone is nowhere near enough. You need a pump powerful enough to drain an Olympic-sized swimming pool in moments. And that is where an invisible and ruthless enemy appears. One capable of turning even the strongest titanium alloy into something that looks like Swiss cheese in just milliseconds. Rocket turbopumps spin at tens of thousands of revolutions per minute, making them vulnerable to a phenomenon known as cavitation. The blades rotate so fast that the pressure in the liquid drops below a critical level, causing the propellant to boil even at extremely low temperatures. This creates millions of microscopic vapor bubbles. As they are carried into regions of higher pressure, they collapse at nearly the speed of sound. Every one of those collapsing bubbles creates a microscopic but incredibly powerful shock wave, generating pressures of thousands of atmospheres. These tiny explosions relentlessly bombard the pump blades, tearing away atoms of metal and gradually destroying the material's crystal structure. In the 1980s, Soviet engineers led by Valentin Glushko encountered the full force of this phenomenon while developing the RD-170, the world's most powerful liquid-fueled rocket engine for the Energia Buran space program. During the first rounds of testing, prototype after prototype exploded within seconds of ignition. Cavitation was so intense that it literally ate away the pump impellers, destroying them almost instantly. The engineers spent years solving the problem. They performed hundreds of complex computer simulations, refined the blade geometry to within hundredths of a millimeter, introduced specially rounded blade profiles, and added tank pre-pressurization to stabilize the flow and eliminate cavitation. Developing this single system took years of work by some of the country's brightest engineers, proving that controlling high-speed fluid flow is one of the greatest engineering challenges ever faced. Once that immense stream of energy finally sends the rocket skyward, the vehicle is subjected to such extreme vibrations that even the slightest misalignment of its control systems can cause an immediate loss of control. A rocket hurtling through the dense lower atmosphere at tremendous speed is extraordinarily sensitive to the smallest changes in attitude or the slightest gust of wind. Mount just one tiny orientation sensor upside down, and the full power of the engines can turn against the vehicle itself, transforming it into an uncontrollable fireball. Every rocket carries highly precise gyroscopes and angular rate sensors that serve as its sense of balance. They are the spacecraft's equivalent of the human inner ear, constantly telling the onboard computer exactly how the vehicle is tilting and how the engine nozzles should be adjusted to keep it on the correct course. But if the computer receives false information about the rocket's orientation, it begins correcting a tilt that doesn't actually exist. The result is a series of increasingly violent maneuvers that can tear the vehicle apart under the enormous aerodynamic forces of flight. That is exactly what caused one of the most spectacular space disasters of the 21st century. In July 2013, a Proton M rocket lifted off from the Baikonur Cosmodrome. Within seconds, it began drifting off course, swaying violently from side to side before rolling over completely, bursting into flames and crashing just a few kilometers from the launch pad in a massive explosion. The investigation stunned experts. During assembly, 3 of the rocket's 6 orientation sensors had been installed upside down. To force them into place, the technician had applied enough force to hammer them in, ignoring the alignment arrows and the guide slots that were specifically designed to prevent incorrect installation. As a result, the onboard computer believed the rocket was tipping over. It tried to correct the non-existent problem and, in doing so, steered the vehicle straight into the ground, reducing a project worth hundreds of millions of dollars to debris. But even when every sensor is installed perfectly, a rocket still needs an extraordinary level of control authority to continuously adjust its course while fighting unpredictable winds high in the atmosphere. Imagine trying to steer a massive steel pole flying at the speed of sound using nothing but the slightest push of air. At high altitudes, where the atmosphere becomes extremely thin, conventional wings and control surfaces are practically useless. Instead, the rocket has to steer by manipulating its own exhaust plume. To do that, engineers use a technique called thrust vector control. Rather than deflecting airflow with fins or rudders, they pivot the engine itself, changing the direction of the exhaust. It's much like balancing a broomstick on your fingertip. If it starts tipping to the left, you quickly move your hand in the same direction to keep it upright. Massive hydraulic actuators, operating at pressures of hundreds of atmospheres, must tilt the roaring engine by fractions of a degree in response to commands from the flight computer, all while fighting the enormous force of the engine's thrust. In 2010, the private company SpaceX faced this challenge during the first demonstration flight of the Falcon 9 rocket. The engineers had to prove they could precisely control the massive first stage, not only during ascent, but also during its return from space. The rocket relied on a sophisticated combination of gimbaled engines, deployable grid fins that acted as aerodynamic control surfaces in the upper atmosphere, and tiny cold gas thrusters that rotated the massive booster in the vacuum of space. As the stage re-entered the dense layers of the atmosphere, the grid fins were subjected to extreme heat and enormous aerodynamic forces, pushing the limits of what the metal could withstand. Even the slightest delay in those control systems would turn a multi-million-dollar rocket into an uncontrollable spinning mass of metal, doomed to destruction. This incredibly complex balancing act is coordinated by the rocket's digital brain, which, during ascent, faces an invisible but extremely dangerous threat from deep space. At altitudes of tens of kilometers, where Earth's protective atmosphere has grown thin, the rocket's electronics are exposed to relentless cosmic radiation. A single software error, or even a single bit of data flipped by radiation, can instantly turn a perfect launch into a catastrophic failure. The flight computer performs millions of calculations every second, constantly updating the rocket's trajectory and controlling the flow of propellant. If a high-energy particle strikes a processor transistor, it can flip a binary 0 into a 1, causing the software to issue a completely irrational command, such as suddenly steering the engines to their maximum deflection. A software failure of this kind destroyed Europe's newest Ariane 5 rocket during its maiden flight in June 1996. Just 37 seconds after liftoff, the rocket's onboard computer suddenly failed, sending a command that drove the engine nozzles to their maximum angle. The massive vehicle immediately veered off course, encountered enormous aerodynamic forces, and broke apart under the stress just 1 second later, triggering its automatic self-destruct system. Investigators later discovered that the accident came down to a single line of code. The flight computer attempted to convert the rocket's horizontal velocity from a 64-bit floating point value into a 16-bit integer, but the velocity was too large for the legacy algorithm, which had been carried over from the previous generation of rockets. The software crashed, and because the backup computer was running the exact same code, it failed in precisely the same way just moments later. The disaster forced engineers to completely rethink how mission-critical software is tested, making code reliability the highest priority in modern rocket development. Having learned from failures like these, today's engineers have gone even further. They have taught computers not only to place payloads into orbit, but also to perform astonishing feats while bringing massive rocket stages safely back to Earth. Landing a vehicle weighing dozens of tons after it has fallen from space at thousands of kilometers per hour onto a small floating platform is like dropping a heavy brick from a great height and expecting it to land perfectly on its narrow edge. Even the slightest delay in engine ignition or the smallest error in the vehicle's attitude can turn a multi-million-dollar spacecraft into a pile of scorched metal in a fraction of a second. To make such a landing possible, engineers rely on one of the most demanding maneuvers in rocketry, known as a suicide burn. The booster falls tail first at tremendous speed and ignites its engines only at the very last moment, when just a few kilometers remain before touchdown. An engine designed to lift hundreds of tons is simply too powerful for an empty, lightweight booster. That means the rocket cannot hover and gently settle onto the ground. Instead, it has to reduce its speed to exactly 0 at the precise instant its landing legs touch the pad. In 2020 and 2021, SpaceX tested prototypes of its massive Starship launch system in Texas, working to master one of the most difficult maneuvers in rocketry, the dramatic flip before landing. The SN8 and SN9 prototypes performed flawless climbs to an altitude of 10 kilometers. They then shut down their engines and descended horizontally, using 4 large flaps to control their fall. But during the final flip back to a vertical position, the engines were starved of propellant. Centrifugal forces pushed the liquid fuel away from the feed lines, leaving the engines without enough pressure to complete the landing burn. Both vehicles slammed into the concrete at high speed and exploded, leaving behind nothing but towering clouds of black smoke and a stark reminder of just how difficult the challenge really was. It wasn't until the third attempt that the SN10 prototype achieved a soft landing. Even then, a fire that continued burning after touchdown caused the vehicle to explode just a few minutes later. These tests demonstrated that modern rocketry is an endless battle against the laws of physics, where every millimeter of the design can determine the fate of an entire mission. The road to the stars is built on thousands of extraordinary engineering solutions. And once you understand the immense effort behind every launch, every rocket lifting off the pad begins to look like a true technological miracle.